Before getting to the meat of this clip, I'm going to take a minute or two to refresh your memories on the basics of TCP/IP networking architecture and NAT addressing. But feel free to skip the next bit if you're already dug in on all that. When that's behind us, though, I'll show you what building VPCs in AWS looks like. This time, by the way, I'll be happy to work in the browser console. The way that looks, right now at least, I think you'll find the experience particularly intuitive and helpful. Okay, so TCP stands for Transmission Control Protocol, and IP stands for Internet Protocol. If those sound a bit broad, almost as if they're trying to describe the totality of the Internet, it's because just about everything we do on the Internet is indeed controlled by these half-century-old TCP/IP protocols. For our purposes, remember that every network-connected device must have a unique IP address. Given that mathematically there can be no more than 4 billion 32-bit IPv4 addresses, and that there are already far more than 4 billion network-connected devices on the Internet, something had to change. The 128-bit IPv6 protocol was eventually introduced to allow trillions of unique addresses. We'll never run out of those. But before IPv6, another brilliant solution was introduced: NAT networking. NAT stands for Network Address Translation, and the protocol sets aside 3 network segments for use in private networks only. Using NAT, your home can have 15 or 20 devices using laptops, smartphones on Wi-Fi, network printers, routers, and maybe a smart fridge or two. But between them, they'll use up only a single public IP address. How does that work? Well, your internet service provider will assign that one public IP to the modem they send you. But that modem will act as a DHCP server and assign each local device a private IP address from one of those 3 network segments. The DHCP server will translate all requests moving between your local devices and internet-based services in a way that leaves those internet services thinking that your device's IP is actually the single public one. But incoming network packets are actually delivered right to your device using its local NAT address. The system really is brilliant, and it added decades of life to the IPv4 system. But once we have NAT in place anyway, it can actually do a whole lot more than just translate local addressing. Which brings us to why we're talking about this stuff in the middle of a course on EC2 instance security in the first place. You see, NAT allows for very sophisticated network segmenting. By carefully configuring addressing and routing rules, you can turn a single local network into a multi-layered, highly secured environment for mission-critical enterprise deployments. Here's an illustration of a replicated environment using public and private subnets from AWS documentation. The only connection with the outside world such a private subnet would have flows through a bastion host and a NAT gateway living in an adjacent public subnet. Forcing everything through these 2 devices lets you precisely control traffic. The bastion host provides a jump box allowing admins to safely open remote SSH sessions on instances running in your private subnets. And the NAT gateway allows services running on your private subnets outbound access to, well, for example, pull software updates. Both bastion hosts and NAT gateways will incur regular usage costs, by the way. I'm going to show you how all this works. From the VPC dashboard, I'll click Create VPC. Right away, I've got a decision to make. Do I want to build just a simple VPC where I can host some resources, or something more complicated? If I go with VPC only, I'll just need to give the VPC a name, select my addressing environments, and I'm good to go. But we're here to test drive the VPC and more option. As you can see, that'll open up an infrastructure preview to the right that shows us exactly what will be created based on the current selections and what they'll look like. Right now, as you can see, we'll get 1 public and 1 private subnet in each of 2 availability zones, and appropriate route tables and network connections to make everything work. Note how each object is automatically given a name that properly reflects the naming structure I specified. All this automatically conforms with security and availability best practices. Let's make some changes to see what happens. An edit of the name with the auto-generate box checked, for instance, will be instantly propagated in the names set for all downstream elements. I could edit the subnet blocks we'll be using. These arrows guide me to changes that make sense, so I don't have to be a world-class expert in NAT networking to keep things workable. I can choose to specify a dedicated tenancy for new instances launched into this VPC, although as I mentioned earlier, that probably won't be relevant for all that many cases. The number of availability zones you configure will reflect the depth of fault tolerance your application needs. The more zones, the less chance your application goes down. Of course, by that same token, the more zones, the more instances you'll need to run and the more you'll spend. You can see that editing this value will have an instant impact on the subnet settings to the right. You can similarly control the number of public and private subnets. The options available will reflect the number of availability zones you selected above. Basically, the UI makes it pretty much impossible to do something stupid, which is something I appreciate. Again, adjusting the subnets will automatically update the configuration to the right. Selecting a NAT gateway will, as you can see here, generate a new object with all the appropriate connectivity built in. I'll drop that NAT gateway for this demo. One last really nice tool is these fields that let us fine-tune the address allocation for our subnets. This would be important if you're planning to deploy, say, large numbers of virtual containers into a couple of public subnets, but nothing more than a handful of database servers in your private subnets. You'll probably need a lot more addresses in the former and fewer in the latter. Okay, let's fire this VPC up. It'll take just a few seconds for all the parts to fall into place. When that's done, I'll be able to navigate to the Your VPC's dashboard to confirm what's now available. When I select the Project 1 VPC, I can see that everything looks the way it should, at this level at least. I'll similarly be able to move to other pages like the Subnets dashboard to confirm that, in fact, we've got a complete VPC environment waiting for us to fire up our infrastructure. We covered a lot of ground in this lesson. We saw how protecting your EC2 instances comes down to some combination of three tools: security groups, IAM roles, and custom-designed VPCs. Security groups can be configured like firewalls to provide protection in layers, allowing you to define who gets access to which resources based on source IP addresses and network protocol. You create IAM policies defining access permissions to specified resources, associate your policy with roles, and attach roles to users or resources, like our EC2 instance that needed access to the S3 bucket. And VPCs can be designed to employ sophisticated routing topologies that expose and block resources to efficiently meet your operational and security needs. Don't forget to follow up on these technologies through the links I've included in the lesson. And please do make use of the code snippets I've included too. There's nothing like trying all this yourself to make the subject really sink in. In the next and final lesson of this course, we'll talk about controlling how your admins can safely connect to your EC2 instances.